In the previous video, we looked at how we can implement this abstract data type called stack using an array. And we saw that if we implement a class called stack, where we use an array as the underlying data structure, using an array as the underlying data structure, then the time complexity that we get for different operations, for push, we got order n time. In the worst case, when we needed to do the doubling, when the array was full and we needed to create an array of double the size and copy everything from the old to the new and all of that. But on average, it was still order one time, constant time on average. Because that case of doubling doesn't happen very often. Okay, so that was push, and then for pop, remember that pop is just decreasing the size. If the size is 0, then you send an error message, otherwise you decrease the size, and that's all we need to do. So it was constant time, order one time. For top, again, you return the element at index size -1, if you remember. And since we have an array as the underlying data structure, it's constant time to return an element at some specific index. And finally, empty, which tells us whether or not the stack is empty. We look at the size. If the size happens to be 0, then the stack is empty. You return true, otherwise return false. And that's also independent from the size or the capacity of the stack, right? It doesn't matter how small or large it is. It's always the same amount of time, so constant time. Okay, so everything seems ideal except this worst case scenario for push that will be slow once in a while. Now, in this video, what we are going to look at is how we can get the same kind of behavior. We have these 4 operations, push, pop, top, and empty, and we get the last in, first out behavior, but by using a linked list as the underlying data structure. Okay, so that's what we are going to see in this video. And again, I'm going to go through the operations one at a time. So remember the create operator, or the constructor for your class called the stack. So in this case, what you need to do is you need to just set the head to null. That's all, right? So if you have a linked list and the head is null, then it means that there is no node, which means that it's empty. So that's how we know that we have an empty linked list, which means we created an empty stack as well. Now, the next operation is push. So we need to know how push will be implemented in this scenario when we have a linked list as our underlying data structure. Let's say I pushed 7 into this linked list that I just created. So I have this head pointer, and at the moment, it's just null, right? So what should happen after this call to push? And in this case, you create a new node and make its key or data to be 7 and the next pointer to be null. And then you say, okay, now head should point to this node. So head is not null anymore, it's pointing to this node. So that's what happens to your linked list after pushing 7, for example, right? Now, if I push again, say 12, I push that to the front of the linked list that I already have. So I have head here. I'm going to repeat the picture and then change it accordingly. Okay, so this is how the linked list looks like before the push. Now I push 12. What needs to happen is, first of all, I need to allocate memory to a new node, and then write 12 here, and also change 2 pointers, namely this pointer, the next pointer should point to what used to be the first node, and also head should point to this new node that I just created, because this is the first node now, right? So basically push in this scenario, when we are implementing a stack using a linked list, push will be push front, right? So push is just the push front operation that we talked about, right? And we know that push front in a singular linked list takes constant time. So our push will be constant time as well, which is ideal. Okay, so that's your push. When you're pushing a new element into the stack, just push that to the front of the underlying linked list. Okay. Now, how about top, the other operation that we need for a stack? So what should happen if I call top here? Okay, and if you remember that in a stack, because of last in first out behavior, top is supposed to return the most recently added key to your stack, which is 12 in this case, right? And that's very simple because we always push to the front. The first node is the one that contains the most recently added key, which means that we just need to return the key in the first node. Basically, we just need to return head arrow data. Okay, and probably you need an if else statement that says if head is empty, then you return an error message and say that the stack is empty, there is no element to return. Otherwise, if it's not empty, you just return the data in the first node, which is, because of the way that we define push, the first key, or sorry, the most recently added key to the stack, right? So in this case, 12. So again, you will see that the time that it takes to do all of this is independent from how many nodes you have in the linked list, because you only look at head and head arrow data. So this is also constant time. Okay, so far everything looks good. Now the next operation that I need to talk about is pop. How do we pop from a stack that is implemented using a linked list? Again, remember that because of the last in first out behavior, pop is supposed to remove the key that is added most recently to the stack, pushed most recently, okay? Which is again 12, this node that contains 12. And again, that is what we called pop front when we were talking about singular linked list a couple of videos before this video, right? So pop is simply pop front. And if you remember, let me do the picture again and remind you about the steps. So at the moment, you have two nodes in your linked list that contain 12 and 7. 12 is the most recently uh, pushed key, and 7 is the first key that we pushed. Now we want to pop. So what I need to do is I need a temporary pointer that points to this node. Then I update head so that it points to the second node. And then I use temp to deallocate the memory that was allocated to what used to be the first node, and then I'm done. Okay, so that's it. Again, you'll see that all of this is independent from how many nodes we have. It's independent from n, which is the number of nodes or the number of elements currently in the stack. And as a result, pop is also constant time in this implementation. Okay, again, if head is null, that's a special case that you have to deal with separately. So you say if head is equal to null, then pop either throws an exception and says you called pop on an empty stack, or it writes an error message that says you called pop on an empty stack. But in any case, that would be a separate case, and all of it can be done in constant time, independent from the number of nodes. And finally, empty is the last operation that we need in our interface for a stack. And empty is just checking to see whether or not head is null. So you just return true if head is null, otherwise false. So return head equals null. So again, it's one line of code, and it doesn't depend how many nodes you have. It takes the same amount of time. So this is also fine. Okay, and that's it, right? So everything is constant time, and there is no worst case linear time like what we had with an array. So no matter what, you can always push pop top and check whether or not your stack is empty in constant time, independent from how many elements you currently have in the stack. Okay, now it may seem like this is absolutely better than the previous implementation, and to some extent that's true because everything is constant time, so we don't have that case where once in a while your push is going to be very slow. But the the disadvantage of using linked list for implementing a stack is the amount of memory that is used, which is almost like double the amount of the memory that is used with an array. And that's because for every key that we have in the stack, we need a pointer that points to the next node, which we didn't have in the first implementation. So to summarize, what we can say is that in terms of the time complexity, this is faster because everything is constant time. So asymptotically, everything is faster. There is no average case. It's just in the worst case, everything is constant time. Where in the previous implementation, we have this worst case linear time. Doesn't happen very frequently, but still, that's a disadvantage. On the other hand, in terms of the usage of memory, the first implementation is more efficient because you just have an array and that's it. But here you have to allocate memory for one pointer per key that you store in your stack.